Hello everyone, my name is Roet-Green and I'm an assistant professor at the Simon Business School, University of Rochester. Today I will talk about queue length information in a tandem queuing system, a joint work with my PhD student, Jean Gray G. So let's start with some motivation. Hopefully you're all doing well, but probably some of you can recall the last time you visited an urgent care unit. Usually, you will go through two main stages. At first, you'll wait to be admitted by the nurse who will take your vitals and ask you some questions about your current health situation. Then, after another period of waiting, you'll be seen by the physician. Now, there's no real value in completing the admission stage. If the expected waiting time for the physician, the extra waiting time, is too long and you decided to leave before seeing the doctor, you simply wasted your time. This setting, which includes waiting for admission and then waiting for treatment, is very common in healthcare services. It also common in retail and food services where the order line is separated from the pickup line. Motivated by the urgent care example, we present a tandem queuing system which consists of two queues located one after the other, the admission queue and the treatment queue. We assume customers observe the queue length of each queue upon arrival to it and then make the decision whether to join or balk. We also assume that both queues are first come, first served. And we ask, how does queue length information impact customer decision and system performance? Our model relates to other papers who examine the influence of queue length information on customers' behavior, followed by the classical observable queue model and unobservable queue model. Other papers also compared between different levels of information, investigating which information model will yield better system performance. Some of the papers also considered the tandem queuing systems. The closest one to us is the recent paper by Hassin and Roet-Green, who studied the decision of customers who travel to a service queue. In this paper, the traveling queue followed by the service queue are modeled as a tandem queuing system with the two main differences from our model. The traveling queue is assumed to be unobservable, and because traveling can happen simultaneously, the traveling queue is not a first come, first serve as in our model. And this, of course, results in a completely different model and analysis. Back to our model, we assume customers arrive according to a Poisson process with the parameter lambda. They observe the admission queue and decide whether to join it or balk. If they decided to join the admission queue, upon completing the service in the admission queue, they will gain no value, but then they will observe the treatment queue and decide whether to join it or balk. By the time they complete the treatment service, they get a value V. We also assume that both services, admission and treatment, are exponential with different parameters, mu A for admission, mu T for treatment. We denote the state of the system as AT, A for the number of customers in the admission queue, T for the number of customers in the treatment queue. And we make the following assumptions. We assume customers are homogeneous. We assume that they're rational, meaning they're maximizing their expected utility. We also assume that they're time sensitive, which means that they have a C cost per unit of time in the system. And to avoid triviality, we also assume that if a customer arrives to a system which is completely empty, the customer for sure will join the system, and this is the condition for that. Regarding queue length information, we assume that the admission queue is always observable, and so is the treatment queue upon arrival to it. Therefore, the treatment queue is simply an always observable queue with a threshold T, which is of course calculated only with respect to the treatment queue parameters. This follows from the assumption that the admission queue waiting costs are considered sunk costs upon completing the admission queue process. So what are the main research questions here? We would like to know what would be the customer's joining strategy if the state of the system is fully available upon arrival, meaning both the queue length of the admission and the queue length of the treatment queue upon arrival. And what would be the strategy of the customer then, and how would it be different than the strategy if customers only have the information about the current queue length and not about the next queue length, which is usually the situation, the case in real life settings. And we want to take these two options and compare them in terms of system performance, throughput, and social welfare, in order to answer the question, is there an advantage in making the system fully observable? And to do so, we are considering two models. The fully observable model, which is the model where customers are observing the entire state of the system upon arrival to the admission queue, versus the partially observable model, where the information is available only about the current queue and not about the next queue. Now, because this is a very short presentation, I would only focus on the fully observable model here. So we already discussed the assumptions of the fully observable model. Let me just add to that that there was an implicit assumption that customers who join the admission queue cannot renege from it. And soon I'm going to discuss why this is actually a redundant assumption in this model. Our goal here is to calculate the customer strategy in equilibrium, and to do so, we start by calculating the predicted treatment queue length based on the current system state. And from that, we calculate the expected utility from joining at a certain state. We take that, and with that, we prove the monotonicity of the expected utility function. We show that customers who join the system never renege, and we will show that the equilibrium strategy is a two-dimensional threshold strategy in this model. So our goal is to calculate the expected utility from joining the queue. And to do that, we start by predicting the probability to find K customers in the treatment queue. If at arrival, there were A customers in the admission queue and T customers in the treatment queue. We calculated recursively, as you can see here, as the probability that there will be a service completion in the admission queue times the probability to find K customers in the system if there is one less customer in the admission queue and one more customer in the treatment queue, plus the probability that there was a service completion in the treatment queue times the probability to find K customers in the treatment queue given that there is one less customer in the treatment queue. Now, this recursive equation that you see here is the main recursive equation that is used to calculate the probability. Of course, there are corner cases that I ignored here, but I don't have time to go over all the cases, so we'll just focus on the main equation. Next, we calculate the expected utility from joining at state AT, which is the expected cost from the admission queue, plus the expected utility from the treatment queue. Of course, the expected utility depends on how many customers you find in the treatment queue upon arrival to it, and you only receive this value and weight in the queue if the treatment queue was below the threshold T. Now, the expected utility is calculated recursively because those probabilities are calculated recursively. And just keep in mind that the expected utility from bulking is normalized to 0. Next, we would like to prove the existence and uniqueness of equilibrium in this model. To do so, we first discuss the monotonicity property of the utility function. We show that when comparing the expected utility of two customers in the queue, the customer who face shorter admission queue or shorter treatment queue at arrival will have higher expected utility. In other words, the fewer customers in the system, the better. And let me illustrate that with the following example, where the threshold of the treatment queue is 5, and we see here a case where we have 2 customers in the admission queue and 4 customers in the treatment queue. With one less customer in the treatment queue, it is clear that everyone are better off. and so on, of course. But what about the case where we have five customers in the treatment queue? Which position is better, the green customer or the red customer? One can think that the red customer has an advantage because there is a higher chance that by the time they complete admission, there will be room for them in the treatment queue. So let's check that. If there was a service completion in the treatment queue, it is clear that the green customer has an advantage over the red customer now. But even if the green customer completes admission and bulks, because of the assumption of exponential service time, the red customer expected utility when they start their service at the admission queue is similar to the expected utility that the green customer had when he was in the same position. And therefore, being farther behind in the admission queue has no advantage. Now we ask whether a customer who joined the system will regret the decision and renege from the system. This is an important question because it allows us to make a realistic assumption on information availability. We can assume that information is available constantly while the customer is waiting in the queue. So let's start from the treatment queue. Because the treatment queue is similar to Naor's observable queue, it is trivial to claim that a customer who joins it never reneges. But what about the admission queue? We need to show that if a customer joins at the admission queue at state AT, they never renege. Now, from state AT, the system can transit to the state where we have one less customer in the admission queue or one less customer in the treatment queue, for which we already show that the expected utility can only increase. But there is another possible transition from state AT to state A minus 1T plus 1, and when we have a service completion in the admission queue and this customer joins the treatment queue. This transition is different than the previous ones because the number of customers in the system does not change. Whereas in the other two cases, the number of customers reduces, which makes it easier to convince that the expected utility will increase. We call this diagonal monotonicity, and we prove in the paper that the expected utility function satisfies diagonal monotonicity. And actually, this is the last mission piece that is required in order to prove that even if information is available constantly, a joining customer never reneges. This brings us to the definition of equilibrium strategy in this model. We show that in this model, there exists a unique two-dimensional equilibrium strategy. And let me illustrate what I mean by that. In the figure here, you see an example of a two-dimensional equilibrium strategy. For every admission queue length A, there exists a threshold, let's call it T tilde, such that for T less than T tilde, customers join, and for T larger than T tilde, customer bulk. Now, in this specific example, we have what we call a sum strategy. Customers join if the overall number of customers in the system does not exceed 3 in this example. Apparently, this is not always the case, as we can see in the following example. Here in the right figure, we see that customers join in states 0, 3 and 1, 2, but they bulk in states 2, 1 and 3, 0. By the way, the only difference between these two examples is that the rate of the admission service in this example is higher. So to conclude, let me go over the main takeaways from this talk. We saw that when customers have access to information regarding the treatment queue length upon arriving to the admission queue, they adopt a two-dimensional threshold strategy. They join the system given the admission queue length only if the treatment queue length is under a certain threshold or vice versa. We also saw that the strategy depends on both queue lengths and not necessarily on the overall number of customers in the system. And last, we saw that customers who join never renege from the system, even if the full system queue length information is available constantly, because if a customer joins the system, their expected utility never decreases. So this concludes my talk. Thank you for listening. And if you have any questions, I'll be happy to take them in the live discussion.